Hello everybody. Today our company, which is nextonix Sudan Berhad, will present about the ethylene production from sweet natural gas. Okay, my name is Nurul Izzah binti Azmi. My matrix number is 197083.
Hello everyone, my name is Ahmed Saleh Mugannib. My mic number is 195011.
Hi, my name is Keshishran Samamiam. My metric number is 198183.
Hi, my name is Nur Safihani binti Ahmad Tazam and my metric number is 198689.
So for the introduction, the raw material that we get for this project is sweet natural gas, and the task that we need to do is we need to produce the 500,000 ton per year of the production. So in our project, the sequences of unit of the process is first is air separation unit, second is OCM reactor, then coolant, quench, CO2 separator, then compressor, and it will be followed by demetanizer, deethanizer, and lastly is the heater. So roughly this is our BFD, which is process selection road, and we start with the OCM and ASU unit and end with the heater unit.
Okay, next reactor is OCM reactor. The function of this reactor is to produce ethylene from methane through OCM stand for oxidative coupling methane. Okay, the assumption that have been made through this reactor is it is a reactive process and it has a fractional conversion of methane of 0.45, has a fractional conversion of carbon dioxide of 0.49, has a fractional conversion of ethane of 0.6, and has a yield of ethylene of 0.25. Okay, this is the chemical equations. This is the reaction that occur in the OCM. But from this 10, we only choose 4 of this reaction, which is number 1, number 2, number 3, and number 7. This is because the rest of this reaction, this equation is being recycled, so we don't need CO and we don't have CO and CO2 reaction. OCM reactor is the first reactor. This stream 1 is basically the natural gas. So mole flow rate in is 3,611, and then we will get the products of 500,000 tons per year of ethylene at the end of the whole process. So this OCM reactor, there is 2 input and 1 outlet. Okay, this stream 2 is the input that we get from ASU, air separation unit, and then stream 3 we go to the cooler, and the outlet of the OCM reactor is 6,556 kmol per hour.
For the air separation unit, the function is to separate atmospheric air, such as the primary component is. So in this project, the primary component of the air is oxygen and nitrogen, and also the function is to increase the production of oxygen. So in my unit, my assumption is 95% purity of oxygen, which is we get from the journal. So this is the SL, and the stream 1, the mole in is molar flow rate for the stream 1 is 6,556, and we end with the 2 stream out, which is the stream that will coming into the OCM is stream 2, and stream 3 we will get rid because the production of oxygen is not much. So next is the cooler unit. So as you all know, the cooler unit is the function is to decrease the temperature of the input. Sometimes we put the cooler because maybe the unit before the temperature is very high, so we need to cool the temperature to prevent from any dangers could happen, such as the machine could explode, or it can be, or maybe because of the next unit of the cooler need the temperature low, so we need the cooler unit. So the assumption for cooler unit is the input equals to output, because of the things that we change is only the temperature, and the cooler unit also non-reactive unit. So as you all can see, the molar flow rate and the mass flow rate is not changed, but the thing that only change is the temperature. So next is the quench unit. The differences between the quench unit and the cooler units is it will decrease the temperature, but in instance. For example, it will decrease the temperature from 600 Celsius into 25. But the cooler will decrease the temperature, for example, from 100 Celsius to 90 Celsius only. So the assumption of quench unit is also same, which as the cooler, which is input equals to output, and it was the non-reactive unit. So this is the Excel and the BFT of the quench.
Okay, hi. How I'll present for the CO2 separator with methyl ethanol amine, MDR. So the function of methyl ethanol diamine is used to remove carbon dioxide gas. It has a equilibrium CO2 loading capacity nearly 1.0 mole per mole amine. It does not react directly with CO2, thus they act as a base as a catalyzing hydration of CO2. The assumption for CO2 separator is the temperature is 100 degrees Celsius and the pressure is 60 bars. Okay, for the MDEA, the stream unit for the inlet is 6,898 kilomole per hour. And it has two outgoing outline stream, which is the second stream which goes to the compressor, which is 6,242.75 kilomole per hour, and the third stream which goes to the removal of CO2 and H2O. It has a volume of 654.797 kilomole per hour. So next is about the compressor. The function of the compressor is to increase the pressure. The assumption is the input equals to output. The temperature of the compressor is 40 degrees Celsius and the pressure is 24 bar. So the block flow diagram of compressor is the stream input equals to output. So stream 1 is 87,060.37 kilogram per hour for input, and output is 87,060.37. So it's the equilibrium and it's the same. Input equals output, but the difference is the pressure, which is the input is 9 bars and the output is 24 bars. Okay, thank you.
Hello everyone. So the next unit is a demethanizer. So what's the objective or the function for this unit is to separate the methane as an overhead product, and also to separate the mixture based on the different volatilities, and also operate it at a continuous steady state. So the assumption of this unit is the pressure is isobarically, and also it's non-reactive unit. So what's going in is going out. So this is my block diagram. This is the block diagram for my unit. So the mole flow rate that going in is 6,273, and with the temperatures with the temperature minus 150 degrees Celsius and pressure 24. So at certain temperature, it will just evaporate. So just like I get 6 species in the inlet stream. So for all of them actually evaporate, but with different composition. So and the methane and the ethylene and the ethane is going out as a liquid in the liquid stream. So the mole flow rate for the liquid stream is 2097 with temperature minus 57 and pressure is 18 bar. So the next unit is the de-ethanizer. So what's the function or the objective for this unit is to separate the ethane as an overhead product, and also get high yield or production of ethylene. Actually, it will not separate it 100%, and we will just do the same assumption and the and everything, even the way that we calculate the mole fraction and mass fraction, everything is the same by using Raoult's law. So the mole flow rate that's going in is 2,970, and at minus we are actually heat the ethanizer. So at minus 48, it started evaporating. So just like it gets separated, and the mole flow rate for the vapor stream is 935, and the mole flow rate for the liquid stream is 2034.82 kilomole per hour. So the temperature for the liquid stream is minus 36, and the pressure is equal to 18. So the way that you use is Raoult's law. So the last unit is the heater, which actually only we want to increase the temperature of the mixture. So assumption is non-reactive unit also. So what's going in is going out. So the mass flow rate that's going in is 57,000 kilogram per hour, and what's going out, it should be the same, 57,000 or 57 kilogram per hour. So the temperature when it going in, it's equal to minus 36, and when it's going out, it's equal to 15. So we increase the temperature. So now I'm gonna talk about the costing and the economic and marketing analysis for the ethylene production. So as you can see here, the first thing that I'm gonna talk is the forecasting. So I get the price for the natural gas, sweet natural gas, and the ethylene from some diagram and some journal from the internet. So I get the price for each one in certain year. Then I do the trending in Excel until like for the next 10 years. So about the costing, I just get the price, the minimum and maximum price for each raw material. We have only two raw materials, which is sweet natural gas that's going into the reactor, and also we have minor oil that's going in and going out for the quiche. So I get the minimum and maximum price for each raw material, and our product ethylene, I just get the maximum and minimum price. So I just calculate the cost, which is you multiply the average price with the amount ton per year. So this is the production of minimum price, and this is the graph that shows it's increased, then it decreased a little bit, then just complete to decrease a little bit. So this is the production with maximum price. So I get increase, then it just decrease a little bit, then increase. So this is the production of the average price. So I just calculate the price for the next 10 years. With the maximum, minimum, and the average price. So the next thing that I'm going to talk about is the demand. It shows from the graph here that the demand of the ethylene is increasing. It's actually increasing around 3.3 to 4.2 every year. This is the increasing of the demand of the ethylene. And actually it is estimated it will reach 200 million ton in 1990 in 2020. So and to me this demand, we need 7 million ton per year increase every year. So this is about the demand. So this is the world consumption of the ethylene. So by the region of the world, so the Middle East, the China, India, and Middle East, they like and also United States. They are the most region in the world that they are consumption the ethylene. So the last one I'm going to talk about the risk assessment. So the risk assessment, I just get the high price, the high price for the natural gas, and high price for the ethylene, and also the lowest price for the natural gas and the lowest price for the ethylene. So I did did every scenario by its own. So also I'm gonna talk about the what if the demand decrease or something. This is something I'm gonna include in my report. So this is basically, so when it is a high natural gas and ethylene price, we get a very high profit, and when it's like with the minimum, we get almost like acceptable revenue or profit. Also, this is the largest global producer of ethylene based on production capacity in 2013. This is actually in 1,000 ton. So this is also the production capacity of the largest producer of the ethylene worldwide, 2014. So it shows that most of them from China and Europe. Thank you so much.
In conclusion, by feeding 544,000 tonnes per year of sweet natural gas, our company can produce 500,000 tonnes per year ethylene with 99.9% of purity, which is good. So the expected price of this ethylene for the next 10 years is between the range of US 2.8 billion per ton and US 5.1 billion per ton.
So for the recommendation, the first one is we did not consider on what to do with the waste such as oxygen and nitrogen from air separation unit, and the carbon dioxide and water at the CO2 separation unit. So the amount of this waste should be given attention and method to handle it for the safety environment. So the second is the costing, which did not include the energy and electricity. So hence the further detailed costing might result in better estimation. So that's all from us. Thank you.